Hello and welcome. I'm Rui from Vassar College in New York. I'm going to present Exploring Wi-Fi Network Diversity for Vehicle-to-Infrastructure Communication, a work performed in collaboration with colleagues from the University of Porto and Carnegie Mellon University. Urban areas tend to feature increasingly large numbers of public Wi-Fi access points, many of which are accessible from the street. A large-scale data collection campaign performed in the city of Porto, Portugal, found that 80% of visited streets had at least one public Wi-Fi access point. So why not try to use them to opportunistically offload some data from moving vehicles? Although a simple idea, this is difficult to implement in practice. One of the challenges is to choose which access point to associate with at each point in time. Multiple may be available, each with its own performance characteristics. If our goal is to maximize the amount of data that we can offload through Wi-Fi, which one should we choose? This is the question that our work tries to answer. There is already a substantial body of work on Wi-Fi AP selection. However, it dates back to the early 2000s. Due to the small number of standards available, at that time deployments were very homogeneous, meaning performance didn't vary significantly across APs. This meant that signal strength was a good AP selection heuristic, as it is positively correlated with the data rate that can be achieved. However, since then, the Wi-Fi environment has changed significantly. With newer deployments coexisting with older ones, we have a variety of different Wi-Fi standards in use. These different Wi-Fi standards use different codings, channel widths, and center frequencies. This leads them to offer wildly different data rates for the same signal strength. Due to this fact, signal strength is no longer a good performance indicator. For example, data that we've collected shows that an 802.11ac network is able to offer data rates of around 200 megabit per second with a signal strength of -70 dBm. This is higher than what can be offered by an 802.11 network, regardless of signal strength. So what do we propose should be used instead? We start by assuming that data rate is a good proxy for the maximum throughput that can be offered by an AP. This makes sense when there's only one client. Since the wireless medium is shared by all clients, if there are multiple, we will need to scale this according to channel utilization. Our work so far focuses on the former case. Our hypothesis is that past data rate observations can help us predict future data rates, particularly when these historical observations were done under conditions similar to the current ones. For example, if a vehicle is traveling at 65 miles per hour southbound on Interstate 87 at mile 3, we can predict the data rate that can be offered by a given AP as the average of all previously observed data rates for that AP under the same conditions. With this in mind, we propose the following approach. First, we create a database of data rate observations. Each observation is annotated with the corresponding AP, as well as the signal quality and client mobility information at that time. This data is then used to forecast the data rate to be offered by each AP over a window of time into the future. All that is left to do then is to pick the AP that maximizes the amount of offloadable data over said time window. In order to test the feasibility of our approach, we collected some real-world data, which we then fed into a trace-based analysis. We placed 3 access points at the corner of an intersection: one 802.11n, one AC, and one AD. We equipped the vehicle with 3 client interfaces, one for each network type, and drove around the intersection, approaching it from every possible direction. We drove a total of around 50 miles, split across 2 days. The results show a clear trade-off between communication range and data rate. The difference is particularly stark between 802.11n and AC and 802.11 AD. The latter yielded very high data rates of up to 2300 megabit per second when compared to 400 megabit per second for AC and 150 for N. However, its range was much shorter than the other networks, at around 40 meters. The animation depicts this well. It shows the number of non-zero data rate samples as a function of geographical location. As we can see, AD could only communicate at very short distances. Now that we have our data, how can we use it to predict future data rates? At a given time t, we forecast the data rate at time t plus I as the average of all data rates observed I seconds after witnessing conditions that match the current ones. Within this framework, we experimented with different algorithms that match conditions using different feature sets, which were chosen based on their correlation with data rate in our dataset. The SQ algorithm only matches signal quality and is therefore the closest to prior work. We then have a series of algorithms that use mobility information. MRD plus SQ matches not only the signal quality, but also the road the vehicle is currently on, as well as the direction it is moving in. MRDP matches only mobility features, the road, the direction of movement, and the position of the vehicle relative to the access point. MRDP plus SQ adds signal quality onto that. Finally, MRDPS matches the vehicle's current road, direction of movement, position relative to the AP, and whether it is stopped or moving. As an example, if we have a vehicle on road 2 at position -4 and heading east, and we are using the MRDP algorithm, we are going to predict the data rate for time t plus I as the average of all the data rates observed for that AP I seconds after the road was 2, the position was -4, and the direction was east. Current conditions are therefore used to determine what subset of data should be used in forecasting. To evaluate our strategy, we split our dataset into 2 halves, the first being used for training and the second for testing. Here we have the results as the mean absolute error as a function of the number of seconds into the future that the forecast pertains to. The mobility-based algorithms outperform the signal quality-based ones. We believe this happened because mobility indirectly captures many different factors, such as the trend of the distance between AP and client and the angle between their antennas. Now that we know how we can forecast data rates, let's see how we can use that information to select an AP. At every time t, for each possible AP, we estimate the maximum amount of offloadable data over a window of a certain length into the future if we decide to switch to that particular AP at time t. The amount of offloadable data is going to be the sum of the forecast data rates over the window into the future. If the AP being considered is different from the one we're currently connected to, an outage period of 0 data rate is used to account for the cost of switching networks. Once we've computed the maximum amount of offloadable data for each AP, we simply select the one with the highest value. Let us see an example. Assume that we are currently connected to AP1, that switching networks implies an outage period of 1 second, and then the forecast data rates for the two available APs, AP1 and AP2, are the ones in the table. The options are to either stay with AP1 or switch to AP2. If we stay with AP1, the amount of data that we can offload will be the sum of the data rates for that AP over the entire window, 1600 megabit. However, if we switch to AP2 at time t, the maximum offload will occur if we then switch back to AP1 at t plus 2. Even accounting for two outages at t plus 1 and t plus 3, this will still yield a larger amount of offloadable data, 1800 megabit. Therefore, our choice should be to switch to AP2 at time t. We compared our data rate forecasting-based strategy against three comparison algorithms. An optimal algorithm, which leverages Oracle knowledge to find a schedule that maximizes the amount of offloadable data, and two simple greedy algorithms. Switch on 0 remains connected to the current access point until eventually its data rate drops down to 0. At that point, it will switch to the AP with the strongest signal. Finally, we have switch on signal quality, which picks the fastest access point that has a good enough signal. Since 802.11ad offers the highest data rates, that is the preferred network. If its signal is not strong enough, then AC is the second choice, with 802.11n being the last resort. We expect our data rate forecasting-based schemes to perform somewhere between the greedy and the optimal ones. But where exactly? Here we have the results of our evaluation. This plot shows the total amount of offloadable data as a percentage of the optimal as a function of the network switching cost, measured in seconds. We can see that all rate forecasting-based algorithms outperform the greedy ones significantly, with the difference increasing with network switching cost. That is because the greedy algorithm's decisions do not take switching costs into account. All forecasting-based algorithms perform similarly, but MRDP and MRDPS perform the best, achieving at least 80% of the optimal. This indicates that signal quality isn't really necessary. On the left here, we have a depiction of how much time each algorithm spent on each network. Both the optimal and the forecasting-based algorithms have a similar allocation, with 802.11ac being the most often used network. Due to its short range, 802.11ad was not used very frequently. However, due to its high data rates, it was responsible for a good share of the total amount of data that the optimal algorithm was able to transfer. Being able to better predict 802.11ad performance would benefit our forecasting-based algorithms significantly. As a conclusion, it is clear that exploring the different trade-offs between communication range and data rate offered by the different networks is key to maximizing the amount of data that we can offload over Wi-Fi. From our results, mobility-based data rate forecasting seems to be a good way of doing just that. In the future, we would like to incorporate the effect of multiple competing users into our scheme. And finally, implement a vehicular Wi-Fi data offloading prototype. Thank you and goodbye.